Hello guys, it's Johnny time and welcome to another smart contract hacking tutorial. Today we're gonna solve together the fifth challenge in Damn Vulnerable DeFi, the rewarder. This is the first challenge with yield farming where we have to find an exploit in the reward mechanism, and it's gonna be so interesting and so exciting. So without further ado, let's get started. So this is the fifth realistic challenge in Damn Vulnerable DeFi. There is a pool offering rewards in tokens every 5 days for those who deposit their DVD tokens into it. So it's very similar to the MasterChef if you're familiar with SushiSwap or PancakeSwap, where you can deposit LP tokens, liquidity pool tokens, and then you get reward of the farm token. So in PancakeSwap it's cake, in SushiSwap it's sushi, and here they try to create similar scenario. Now Alice, Bob, Charlie, and David have already deposited some DVT tokens and have won their rewards. You don't have any DVT tokens, but in the upcoming round you must claim most rewards for yourself. So you don't have DVT or LP tokens to stake in the pool, but you need somehow to get the rewards. How are you gonna do it? We don't know yet, but by the way, rumors say a new pool has just launched. Isn't it offering flash loans of DVT tokens? Okay, so we got a small hint here that there is some kind of pool that offering flash loans in DVT tokens, which we can probably utilize in order to manipulate the reward mechanism and get for ourselves rewards. So now let's head to the contracts folder and see what smart contracts we have to deal with. So this is the contracts folder, and here we have the rewarder, and we can see over here that we have 4 smart contracts. 2 of them are tokens. We have also the flash loaner pool that offers the flash loans, and the rewarder pool, the smart contract that is responsible for the staking tokens and giving us the reward probably. Now let's start with the reward token. This is the most simple contract. It's Solidity version 8, imports ERC20 and Solidity. So we use here OpenZeppelin and Solidity for ownable roles, and the reward token is ownable. Now we have Minter role with role 0. It's probably some kind of a role that comes from the inheritance of the ownable rules. Now we initialize the owner in the constructor, which is the message sender. So the one who deploys this smart contract is going to be both the owner of this token and also the minter. Now the mint function can be called only with the one that owns this minter rule. So we're just gonna mint tokens, unlimited amount of tokens, it receives 2 and amount. So this is a simple ownable ERC20 token, the reward token that we need somehow to get, but we cannot trick this contract because it has very simple functionality and it uses battle tested contracts like ERC20 OpenZeppelin and ownable rules from Solidity. So this is a black box for us. Now the next token is the accounting token. So I assume this token will be used to track how many tokens each user deposited to the rewarder pool. Now it's kind of receipt tokens, like the tokens that you get when you deposit in lending protocols like Aave and Compound. If you're not familiar with lending protocols and you want to enhance your skills, check out the smart contract hacking course, where basically we're going to learn everything, including the basics of DeFi. So you will learn all this DeFi crash course about DEXs and money markets, and we're going to cover so many attacks, both theoretically and also practically, because every lecture will have 2 to 4 exercises where you will have to hack smart contracts and obviously fix them with walkthrough videos like this one. So it's the most comprehensive smart contract hacking course that you can find, including guest lectures from professionals in the field and a Discord community, supportive community, and a certificate. So if you want to take your skills to the next level and become a certified smart contract auditor, check the special link in the discount below, $100 discount link, which will expire soon, so check it out. Now the accounting token has 3 roles, role 0, 1, and 2. This is mint role, snapshot role, and burner role. Now we have one error defined here. This is the R token, we call it accounting token. We initialize the owner and grant all the roles to the message sender. So the rules here, it just just doesn't make sense. Usually it's very centralized because we have one EOA account that gets all the roles, the owner and the other roles as well. We can see that the minter can call only the mint function, the burner can call the burn function, and the snapshot role can call the snapshot function. So we don't use just normal ERC20 token, but we use ERC20 snapshot, so we can get the balance and the supply of the total supply and the balance of specific account in specific snapshots. So at any point in time, we can call, not anyone, just the snapshot role. The account with the snapshot role can call the snapshot function, take a snapshot at this point of time and this block timestamp, and then we can go back to the snapshot and see what was the balance. This is very useful for governance mechanisms and also for such yield farming reward mechanisms. Okay, so we use this kind of snapshot functionality for the accounting tokens, so we can know back in time what was the balance and what was the supply. Now, this is the flash loaner pool contract, which is supposed to give us flash loans in DVT tokens, or in the real life scenario, like the LP tokens that we need to stake in the pool in the yield farming contract. Now, we can say that we use here Reentry Guard, and we use also the liquidity token, which is the DVT token that was described here in the description over here. This is the DVT token, the liquidity token, and we have some errors defined. We initiate the contract with the liquidity token address and we wrap it. And we have one function, which is the flash loan, right? It's protected from reentry. It receives an amount, it checks the balance before, make sure that we don't request a flash loan with amount that is greater than the current balance in the pool, or it will revert with this error. It makes sure that the message sender is a contract. By the way, this check can be bypassed. So if you see something like this in an audit, it's an issue. So you can add here an audit issue comment, and it can be bypassed if we call it from a constructor. So this is a valid issue in auditing contests. It's not going to help us in this exercise, but just FYI. And here we can just transfer, basically we transfer the tokens, the liquidity token, the DVT tokens to the message sender, the amount that he requested, and we make a callback. This is the callback. So we, the receivers, it needs to be a smart contract that implements this receive flash loan with UIN256 with the amount. So we need to implement this function to get this callback and pay back the token to the smart contract, or this will revert here, because here we check that the balance of this smart contract after he gave us the tokens and after he made a callback should be not lower than the balance before. So it basically makes sure that we paid back the tokens after we got them. That's the whole purpose of flash loans. And again, if you don't know what are flash loans and you want like deep dive, fundamental, practical course, check out the smart contract hacking course. Now, the last contract that we want to overview is the rewarded pool, which is where most of the interesting parts are going to happen, because probably the vulnerability relies somewhere there where we need to kind of manipulate the state of the pool. So we have here some constants. Now, the first constant is 5 days, which is the time that we have to basically wait between every round. It was described over here every 5 days, so we can see it here. Now, the rewards are 100 Ether, which is cool. We're gonna stake DVT tokens and get Ether, and we need somehow to get this Ether. It's not gonna be Ether, it's gonna be the reward token, but we count it with 18 decimals, so we use Ether. We have the liquidity token, the accounting token, and the reward token. Here we have some integers like unsigned integers, last snapshot ID for rewards, last recorded snapshot timestamp, and round number, because we count the round and we count the time for every round for distribution of the rewards. And this is the last reward timestamp. So it maps from account to the last time that he received the reward. So we can prevent him from receiving reward twice. Probably we don't know, we're just assuming it because we didn't get into the functionality. Now, this is the constructor. It receives a token, which is the liquidity tokens. It's the token that need to be staked in order to receive rewards. And as you can see in the constructor, we actually deploy both the accounting token and the reward token. So as you remember, we are the deployers, which means that these smart contracts is going to be the owner and the minter and the snapshot and everything basically of this reward and accounting tokens, because the message sender is going to be this contract, which is going to get all the rights. And the first thing we do is record snapshot. Record snapshot is this function, which basically gonna record the first snapshot and make officially the first round. It's gonna record the ID, which is the accounting token snapshot, which is gonna start from 1, snapshot ID 1. Then we're gonna take the current timestamp. This is the time of this round, when this round started, and the round number plus plus. By default, it will start from 0, so plus plus, it means it's gonna be round number 1 after construction. So we saw what happens upon construction and what is the record snapshot function. Now let's see what happens when we deposit money into the contract. We send the amount and we need to be not 0, so we cannot trick the contract and send some kind of 0 amount. Then it's gonna mint for us the accounting token, like I assumed before. So every time we deposit the liquidity, the DVD token, we get this accounting token, which basically worth nothing, but it's just gonna be used for accounting to see how many tokens we deposited, some kind of receipt tokens, and to calculate the rewards. Now, right after deposit, we call distribute rewards function. So before we actually basically transfer the tokens from the user to the smart contract, the liquidity tokens, we distribute rewards first, which is a bit odd. Why don't we transfer first the tokens and then distribute rewards? But we will get to the distribute rewards function later. And then we use the safe transfer lib, safe transfer form function to get the liquidity tokens, the DVD tokens from the message sender to this contract. We need to make sure to approve it before, or this will fail. So we need to approve the contract to spend our tokens. Now withdraw, we just pass the amount and we try to burn the accounting token. Now, if we never deposited first, we don't have account tokens, so this will revert. So we cannot trick the system by just trying to withdraw tokens without depositing, because this will revert. And then we transfer the liquidity tokens. So we burn the accounting token and we pay back the liquidity token to the user, to the message sender. So there is no need to check like how many tokens were deposited, because if we didn't deposit, this will revert. Now that's where the interesting part starts. This is the distribute reward function. So let's see what happens. It's a public function, anyone can call it, and what it does first, it checks if it's a new reward round, okay? Let's see what is new reward round, what it means. So if block timestamp greater or equal than the last recorded timestamp plus 5 days. So every 5 days we make a new round, and if it's a new round, basically what do? We call the record snapshot again. So actually, a very useful thing to do is to draw a diagram. So as you can see here, I use Excalidraw to draw the diagram. And this is a round, so it could be round X, 1, 2, 3, 5, and it's from last recorded snapshot timestamp to last recorded snapshot timestamp plus reward round minimum duration, which is 5 days. So if we are, just ignore this kind of thing. This is regarding the exploit that we're gonna do later. But basically, if this time passes, then let's say we are here, then it means that it's time for a new round. It's a new rewards round because the block timestamp is greater than this thing. So the block timestamp, let's say we are here, it's greater than this, which means that we set a new round, which means that we update the last recorded snapshot timestamp and it will move forward and forward and forward. So this is how we count the rounds, and I highly recommend you use this kind of diagrams, apps, or maybe use a notebook to draw it down to get better understanding about how the protocol works. Now that we understand how we calculate the rounds and record new snapshot, let's see how we actually distribute the rewards. So first, we're gonna get the total deposits. What are the total deposits? Basically, the total supply of the accounting tokens. So you can see that we use total supply at, so we can basically refer to the last snapshot time or snapshot ID. We don't get the current total supply, but we use the snapshot functionality to get a total supply in this particular snapshot. And we can also get the current balance of a particular account at a specific snapshot ID. And this is going to be exactly the amount deposited by the user. So we have the total deposits and the amount deposited by the user. Now, if the user did not deposit anything or there are no deposits at all, then we're going to do nothing. So that's why we have this if statement here. And this is where we calculate the rewards. So the rewards are going to be the amount deposited by the user, right? Amount deposited, as you can see, a balance at of this account, Muldiv, basically we use this library over here, safe fixed point mathlib by Solidly, and it's gonna do safe math, and it's gonna do safe multiplication and then division. So we're gonna multiply amount deposited by the reward, which is 100 ETH, but in the reward token, divided by the total deposit. So let's go back to the diagrams, as you can see. So it's going to be the user deposited multiplied the reward, which is a constant number, divided by total deposited. So we do not control the reward because it's a constant number. We do not control the total deposited, but we do control the user deposited. So the more we deposit, the more rewards we get. And we can already see first issue over here. It doesn't take into consideration how much time we stake the token in the contract. So it just takes into consideration only the amount that we deposit in this point of time, in this snapshot, which is a big no-no, a big red flag for staking contract, because it needs to take into consideration for how long we stake the token. Now, if the rewards is 0, then we don't do anything. And also we check that we didn't retrieve the rewards. So has retrieved rewards is simply going to check that simply we did not retrieve rewards in this round. So we cannot retrieve rewards twice in the same round. And this is the last time that we retrieve the reward. It should be greater than the last recorded snapshot timestamp and lower than the end of the period, which is the recorded timestamp plus 5 days. So if we go back to this timeline, if we withdrew the rewards once in this timeline and we try to call it again while we're in the same round, then the transaction will be reverted because it knows that we already withdrew our rewards. Now, if we didn't withdraw rewards, then it's going to mint for us the reward token, which is the jackpot. This is what we need, right? Remember, this is what we need in this exercise to get the rewards. And it's going to update the mapping. So also, by the way, there is no checks effects interactions pattern here because we can already write it, audit issue no CEI, because it mints token, it does an external call, and only later it updates the state. So it would be beneficial to change the order here. Also here, the reward, we can hear here another audit issue, doesn't take into consideration deposited time, right? So we have here two issues that we can already report to the protocol, but we need to actually exploit it to pass the challenge. So now that we have a context of the whole contract and we see how it works, we need to come up with creative ideas of how we can utilize the flash loan in order to manipulate the reward pool. And if you're still not sure, I also made these diagrams. So we have the flash loaner pool smart contract, and it has the liquidity tokens that we need to deposit in the rewarder pool contract. And with the user, we can get those liquidity tokens as soon as we pay them in the same transaction. So we get those liquidity tokens using flash loan, but we need to pay them in the same transaction. And this rewarder pool contract, we can deposit the liquidity token, it will mint a counting token, and we can basically withdraw a liquidity token, it will burn the accounting token, and if we call the distribute rewards, based on our deposited liquidity token, we will get the reward token. Now, everything makes sense, we have diagrams, we looked at the smart contracts, and it's time to come up with an exploitation. So our plan is going to be depositing, getting the rewards, and withdrawing the money. But we don't have DVD tokens, so we will have here to do a flash loan, right? We'll have to take the DVD tokens from the pool in a flash loan and in the same transaction pay back, right? So we have to pay back the loan after we deposited, we got the rewards, and we withdrew the tokens from the pool rewarder contract, and we need to pay back the tokens to the flash loan smart contract so the transaction will not be reverted. Now that we have the plan already and we understand the whole system, the whole state, it's time to write our exploit. So I'm going to head over to the player contract and player contract folder and create a new malicious smart contract. I will call it attack the rewarder.sol. Now we have to create a malicious contract because if not, we will not be able to receive the flash loan. So we will use Pragma Solidity and it will be 0.8.0, and then we will define a new contract. Let's add this here so it will not scream at us, and it's going to be attack the rewarder. This is going to be our malicious smart contract. Okay, now we need certain state variables. Okay, we need to know a lot about certain things in this smart contract. First of all, it's going to be the flash loan pool, so we'll have to write an interface for the flash loan pool so we can interact with it, request flash loans, pay back the flash loans. So flash loan pool immutable, and it will be pool. Let's call it flash loan pool. Okay, and let's define here an interface flash loan pool, and we will also need to define the reward pool. So interface reward pool, and we will create another state variable. It will be immutable reward pool. Now we need to be aware of also of the liquidity token or the DVT token. So it will be IRC20 immutable. Let's call it liquidity DT token. And we will copy from here. Let's just import the OpenZeppelin ERC20 token. So I'm just going to copy it from here. So this is going to be the IRC20 token by OpenZeppelin, the interface, so we can just use it. And we also have the reward token that we will need to work with. So we're working both with the liquidity token and with the reward token, because we'll have to send it back to the player once we get it. And we will define also the address of the player. So it will be immutable player. Now that we have all the state variables, let's write the constructor. And the constructor will receive all the following parameters. First of all, it will receive the address of the pool. It will receive the flash loan pool, flash loan pool. It will receive also the address of the reward pool, right? The staking contract. It will receive also the address of the liquidity token. Let's just copy it over here and break the line so it will be more readable, liquidity token, and also the address of the reward token. So now we received all the state parameters and it's time to set them. So it will be flash loan pool equals flash loan pool with the address of the flash loan pool. And we will do the same for the reward pool. And we will do the same for the liquidity token. So the liquidity token will be IRC20 of the liquidity token. And the reward token is going to be the reward token. And the player, who is it going to be? Very simple, the message sender, right? Player equals message sender, the one who deploys this smart contract, because eventually we want to add some access control. We also want to send the reward tokens back to the player. So we'll have to define here the player account. Now let's define the attack function that will start and initiate the attack. So function attack, and it will be external. And let's see, in order to initiate attack, we need basically to call the flash loan to request the flash loan for the liquidity tokens, for the DVT tokens. So we will copy it for the interface. So we will add it for the flash loan pool. We can remove the non-reentrant modifier and add a semicolon. So now we have the interface for the flash loan function, where we can call the flash loan pool dot flash loan. The amount, which amount we want to get from the pool. We're going to get all the balance of the liquidity token that the pool has, all the DVT tokens basically of the pool. So we're going to use the liquidity token contract dot balance of the address of the pool. So it will be address of the flash loan pool, right? So we get all the balance of the flash loan pool, but that's why we actually need to save the liquidity token, so we can use the balance of function to get a balance of the pool and request everything using this flash loan. Now remember, once we execute the flash loan, this callback will be triggered, so we need to implement this function that receives an integer. So I will define a new function receive flash loan. This will be amount and it will be external. And first we want to define some access control. So we'll do require. We want to make sure that our contract is secured to make some basic OPSEC. So message sender should be the pool. It will be the address of the pool, the flash loan pool, flash loan pool, this one. And we also want to make sure that the TX origin is the player, right? Origin equals the player. We don't need to wrap it with address, just player. Okay, so we have some access control in place. Now we need to do the following scenarios. So we need to deposit tokens. We got the tokens already because this is the callback. So we already have the DVT tokens. We need to deposit them. Then we need to get the rewards and we need to withdraw. Okay, so this is going to be our attack sequence. So first of all, if you remember, in order to deposit, we need to approve the pool contract to spend our token, the rewarder pool contract. So that's exactly what we're gonna do. We're gonna call the liquidity token dot approve function. The spender is gonna be the address of, this time not the flash loan pool, but the reward pool, right? And the amount is going to be the whole amount that we just received because we want to deposit all the tokens to maximize our rewards. Now that we approve the token, we can call the deposit function, but first we need to implement the interface. So I will call this, I will copy this line and add it to our interface and change it to semicolon. And now we can call the deposit function. So it will be rewarder pool dot deposit and the amount is going to be the exact same amount. Now the next thing we're going to do is call the distribute rewards to make sure that we get the rewards after we deposited the money. So I'm going to just copy the exact same thing here, add it to our interface and add a semicolon. It should be external because it doesn't know what is public when you write interfaces. So let's call this function external and let's call this function. So it will be reward pool dot distribute rewards. Now, once we got the rewards, hopefully we want to withdraw the money because we want to pay it back to the flash loan pool, right? So we're going to get the interface for the withdraw function and add it to our interface of the pool and semicolon as usual. And again, reward pool dot withdraw with the same amount. Now we got back the DVT, the liquidity tokens, and it's time to pay back the pool, the tokens. So I'm going to do liquidity tokens, the dot transfer. The 2 is going to be the address of the flash loan pool, and the amount is going to be the same amount. So this is basically pay back the loan. And what do we have to do? We also need to send the reward tokens to the player account because probably he's the one that's supposed to have the reward tokens, not this contract. So we cannot keep the tokens in this smart contract. So payback loan and send reward tokens to player. So here we pay back the loan and we want to do reward token dot transfer, and 2 will be a player. And how many tokens? We don't know how many tokens we got. We simply want to send all the tokens that this smart contract, this malicious smart contract has, the whole reward tokens. So we're going to do reward token dot balance of it's going to be address of this. So we're going to check the balance of this smart contract because we don't know how many reward tokens. We can actually calculate it, but the simpler way is just to call the balance of function and send all the reward tokens to the player account. Now it seems legit. It looks very good exploitation contract. We have a very nice malicious contract. We basically implemented all the pseudocode that we planned before in the diagram. And now it's time to go to the test file and see how we can deploy this malicious contract and execute the attack. So this is the test file. This is the scenario of the exercise. I'm not going to go through everything. We have here some constant of use, some accounts, some definitions. We have here all the accounts, you know, the Alice, Bob, Charlie, David, and player. We are the player. Here we get all the factories. We deploy the contracts. You know, we send the liquidity tokens to the pool. We send the reward tokens and everything, yada, yada, yada. Make sure that all the roles are correct. right? We do some tests with the users, so the users deposit money and we make sure that they get the rewards. We gonna advance 5 days so depositors can get rewards, right? So this is how we can advance the EVM in Hardhat 5 days. It's kind of like cheat code, like in Foundry. And here we make sure that each depositor gets the rewards and that the balances are correct. Now, this is where we need to execute our code. And this is the state that we need to achieve. So the round number should be 3. Which means that we need to push 1 round forward. So we're gonna do this. We're gonna basically fast forward the EVM before we start the attack. So we simulate like 5 days passed after Charlie, Bob, and whatever deposited their tokens. And then now here we check that the users got less tokens that they are supposed to get. So we make sure that they got less tokens, they got less rewards, but we made to make sure that the player account got most of the rewards, right? And here we check that the reward that the player got is almost the whole rewards that were minted so far. The whole rewards that there are, and it should get like most of the rewards and exploit the logic in the pool to get the money. And we also make sure that the balance of the DVD tokens of the player and both the flash loan pool wasn't changed. So we didn't do anything fishy and we still don't have the DVD tokens because we should get them and pay them back to the pool. Now we don't have much to do here in the execution, just to move 5 days in time and deploy our malicious contract and call the attack function that will start all this domino effect and the whole attack that we just implemented in the smart contract. So I'm just gonna deploy the contract. So this attacker contract equals await and await. Now we will use the factory ithers.get contract factory. The contract is gonna be attack the rewarder. So let's just copy the contract name, attack the rewarder, and the account will be the player. Now we're gonna use this to deploy it. So we will deploy it with the whole parameters. The first parameter should be the flash loan pool. So it will be address of where is the pool, where is the pool? It should be here, flash loan pool. So address, not address, but flash loan pool dot address. Then the next one should be the rewarder pool dot address. I think so. Yeah, reward pool. Then the liquidity token. So it will be liquidity token dot address. And the last one should be the reward token. So it will be reward token dot address. Now that we deploy the contract, we just need to await and call the this attacker contract dot attack. And everything will happen basically, right? Because once we trigger the attack, we request the flash loan, we receive the liquidity token, we approve the reward pool contract to spend it, we deposit, we distribute rewards, we withdraw, we pay back the loan, and we send the reward token to the player, and eventually we should achieve this required state. So now it's time to check our exploit. This is the money time. Now cross your fingers and we're gonna run yarn the rewarder. Let's see what happens and if we are able to get a state. And yes, congrats guys, we were able to exploit the rewarding system. We were able to get most of the rewards in the pool. Even though we don't possess any DVD tokens, we utilize the flash loan pool to get those tokens. Congrats, you learned so much in this CTF and in this exercise. And if you want to learn more, make sure to subscribe to the channel, watch the other solutions for non-vulnerable DeFi and other useful content to level up your skills in smart contract hacking and auditing. Thank you so much, and I will see you in the next video.